Hi there, thanks for tuning in. I'm presenting HarvestNet, which is a data set for detecting smallholder farming activity using harvest piles and remote sensing. I'm honored to share our work here, and I'm glad you could join us. So just to begin, just wanted to thank the team, the amazing people that have worked on this project. We're a group of people from Stanford, Waterloo, and Kent University collaborating in Sustain Lab under the supervision of Stefano Erman and David Lobel. So some context on the problem. What we're looking at is the field of smallholder farming. This is the major type of farming in the world, and it produces more than half of the food calories. In regions such as sub-Saharan Africa, um, 80% of farms are under 2 hectares of size, so they all qualify as smallholder farms. So mapping these types of farms is really important for tracking sustainability measures, and we are so far not very good at doing these type of detection. Some current existing approaches are more algorithmic in nature, and there are also some machine learning based approaches. The most common ones involve looking at the temporal growth patterns of different crops over time, and also looking at field boundaries to demarcate actual cropland. The issue with these sort of approaches is that weeds and wild vegetation often exhibit similar growth and spectral patterns resembling cultivated crops. And the type of landscape that smallholder systems are in is extremely diverse, and it's very hard to accurately demarcate field boundaries in these areas. So what we have actually are some harvest piles that we could look at. So these are made during the harvest season in these smallholder farms. This is common to smallholder systems throughout the world at the end of the harvest season, and these crops are gathered into piles of 3 to 10 meters before threshing. And these footprints are present until after threshing, and they finally disappear when the land is prepared for the next season. And unlike other signs of human occupation, piles are a much more dynamic indicator of active um, farming. Here are some remote satellite images of harvest piles. You can see that they vary greatly in terms of shape, density, and distribution, and they are in completely very different sorts of land, and this is all in Ethiopia. Here are some more examples of harvest piles and various stages of harvest pile activity. What we're focusing on is the country of Ethiopia, which has the third largest agricultural sector in Africa based on its GDP. We focus specifically on the lowlands in Tigray and Amhara because these areas have historically been mapped incorrectly. They also have a variety of different agroclimate zones. And these areas, the crops in this area are mainly grains, and these piles can be observed as early as October and stay on the land as late as May of the next year. Our contribution is that we propose a framework to detect farming activity through the presence of harvest piles. We created a data set of 7,000 labeled SkySat and PlanetScope images. These are binary labels, and this is all in Tigray and Amhara during the harvest season throughout 2020 to 2023. We also sent a ground team to collect around 2,000 ground truth labels, and we also have curated around 150,000 unlabeled SkySat images. We also document a pipeline for balancing between scale, quality, and consistency. We then benchmark our models on HarvestNet in general accuracy metrics, and then we also produced a qualitative evaluation of models trained on our dataset by comparing against the current state-of-the-art land coverage map, ESA World Cover. So what we did for actually gathering the satellite images was we chose a geographical scale of 250 by 250 meters. We found this was a good fit to allow us to get good enough spatial resolution while not covering a large enough piece of land with a decent resolution. We look at two image resolutions, which is zero point 0.5 meters by SkySat and 4.77 meters per pixel by Planet Labs. Essentially, you need a high enough resolution to see harvest piles, but you need low resolution images because they are a lot more abundant and easily accessible, in both in terms of space and time and money. To label, this is a novel task, so we needed to hand label our data set to train our models. We used the guidance of experts who are familiar with harvest piles and their appearance in remote images in these areas. We gathered these satellite images. We then used Mechanical Turk to filter out the obvious negatives, and then the experts labeled the positives. During the labeling process, there was also quite a few different edge cases, and so that made it a lot more challenging where we had to restart our whole process. Here's some examples of that. In the first three images, you can see that these are dots that look very similar to harvest piles, but they are not. They are various examples of attributes that come from early stages in harvest or the footprints that are left by the piles after they are cleared out. The bottom three images are false positives, so these show some examples of dots that look like harvest piles but actually are not. We also see that there are three main stages of harvest, and this is harvesting, piling, and threshing, and the footprint looks completely different in these three sort of stages. So what we do is we classify yes as harvest activity when it is any of these three stages of harvest. What we use to ensure dataset size and quality is our own pipeline, where we have experts distill knowledge to the coordinators who then create tasks for Mechanical Turk workers. These Turk workers, we have two of them, and when they disagree, the coordinators make the executive decision. These filtered images will not have the obvious negatives, and then we finally pass them to the subject experts for final labeling. To ensure that our data set covers between train and test has similar distribution without overlapping geospatially, we grouped images that were overlapping into groups using a graph traversal algorithm, and then we separated distinct groups between the different data sets. So we can see here that the distribution shows generally that the train and test cover around the same distribution. We also sent a ground truth team to collect some survey data in March of this 2023. And yeah, we gathered around 2,000 unique labels. However, due to the ongoing armed conflict, the team was unable to visit some areas in Tigray that were covered by SkySat. So we had to combine the ground truth data with PlanetScope images, which were more diverse but were in lower resolution. To evaluate our models, we pass our images through some common ML models to get the probability of farming activity. So these are some of the common models that we used. Essentially, these are various combinations of image CNNs or SWIN transformers or autoencoders. And then to evaluate on these models, we center cropped our SkySat images to 512 by 512, and we center cropped this PlanetScope to 56 by 56 to get the same geospatial resolution. These images are then scaled to fit the models. So these are some of the results from our quantitative evaluation. We see that the SWIN autoencoder and ResNet 50 are great on this, and they achieve a pretty good accuracy. Results on table 2 are the ResNet model on our ground truth data collected by the field team. So here's some qualitative evaluations. We compare with the ESA land cover. So you see in these rectangles, our experts identify these areas as missing harvest activity, even though they actually did have smallholder farms. So our models were able to detect that here. Here's some closer view of some things that we were able to detect. And here is a table that describes mainly the first column that the samples that ESA classified as negative while we classified as positive. So that's we find 56,000 new hectares of smallholder farms there. We realize that there is potential bias here. So labelers may be biased in their interpretation of piles, and our models exhibit a bias towards processing piles with larger shapes and colors. We also chose specific areas, and there was also bias in where we collected our ground truth data. Our dataset is also quite limited. It's simply binary labels on fixed dimension areas, which yield a lower spatial resolution. This is mainly to allow us to gather a large enough data set when we were just doing manual labeling, but that's something that can be improved. We would like to incorporate time series data for harvest pile detection as a potential next step. Moreover, models trained on HarvestNet indicate potential applications in other agricultural settings, such as hay bale detection in North America. So to conclude, we present HarvestNet, which is the first dataset for detecting farming activity using remote sensing and harvest piles. We introduce labeled SkySat images and PlanetScope images, as well as ground truth images collected by a team. We documented our process for building the dataset and showed that models trained on HarvestNet were able to perform really well for classification and were able to beat ESA in detecting more land in smallholder areas. So overall, this has been a really great project and we are quite excited by the results. We hope you are too, and we would be open to any chats of collaboration, or if you have any questions, feel free to reach out to us. Thank you so much for your time.